Hello everyone, welcome to my presentation on the concepts and applications of derivatives. Firstly, let's start with a brief introduction to the derivatives. A derivative measures how something changes. It tells us how quickly one thing is changing in relation to another. You can think of it as a slope of a tangent line at a point on the function, as shown in the figure. Derivatives are commonly written using various notations as listed below, and the most commonly used notations are the first two, f prime of x and dy by dx. The other notations are used depending on the context and the field of applications. I believe derivatives are the cornerstone of calculus as they form the foundation for many of its key concepts and applications. They help us understand the model changes, making them an essential tool in mathematics. The history of derivatives spans centuries, beginning with Archimedes in the 3rd century BCE, who explored rates of change in his study of motion and geometry in ancient Greece. In the 12th century, Pascal II introduced early differentiation concept in his work Derivati, focusing on instantaneous motion. In the 17th century, Newton and Leibniz formalizing derivatives, describing rates of change and slope of curves laying the foundation of modern calculus. Later, in the 19th century, Cauchy rigorously defined the derivatives using limits, providing a solid mathematical framework. Here is the basic definition of a derivative. If a function fx is defined on an open interval around x equals x1, the derivative at x1 is given by this limit expression. For this derivative to exist or differentiable, the limit must have a well-defined value, which means it can't be infinite or undefined. Watch out, these are all non-differentiable functions at certain points. Additionally, for the derivative to exist at a point, the limit must be the same from both sides. If the left-hand and right-hand limits are not equal, the derivative does not exist at such point. For example, as shown in this plot, the absolute value function is not differentiable at x equals 0. The geometric intuition of the derivative is that it represents the slope of the tangent line to the curve of a function at a given point. This describes the instantaneous rate of change of the function at that point, which we can calculate using this limit formula. Another way to think of a derivative is to consider it as the limit of the average rate of change as the interval shrinks to 0. We can better understand this concept through the animation diagram shown here. As you can see, we can define any function here, represented by the black curve. The green line represents the tangent line to the function at the red point, and now its slope is 1. The red dashed line is the secant line passing through the red point and blue point, and its slope is currently 0. The slope of the secant line represents the average rate of change between the red and blue point. As the blue point moves closer and closer to the red point, the secant line approaches the tangent line. Ultimately, the average rate of change between the red and blue point infinitely approaches the slope of the tangent line at the red point, which is 1. This is exactly the derivative at the red point. It's also important to know that if a derivative exists at a point, the function must be continuous at that point. Let's explore an example of applying derivatives to a quadratic function. For this function, the first derivative is 2x, which tells us the slope of the tangent line. At x equals 0, the slope is 0, making it a stationary point. Next, we compute the second derivative, which is a constant positive value 2. This indicates that the function is convex everywhere. Therefore, by using derivatives, we determine that x equals 0 is a local minimizer of this quadratic function. Derivatives are incredibly powerful tools with a wide range of real-world applications. Firstly, in physics and engineering, derivatives measure rates of change, such as velocity and acceleration. These concepts are crucial for designing vehicles and machinery. A car's speedometer and acceleration provide practical examples of derivatives in action. Additionally, in economics and finance, derivatives reveal how profits and costs fluctuate with changes in output. These insights plays a vital role in making business and investment decisions, such as analyzing interest rates and market trends. Furthermore, in medicine and biology, derivatives track population growth rates and changes in drug concentration over time. This application contributes to better medical treatments and a deep understanding of disease patterns. Finally, in machine learning, derivatives drive optimization algorithms like backpropagation. These allow AI models to minimize errors and improve their accuracy, making them more efficient and effective. These examples highlight just a few ways that derivatives shape modern science, technology, and innovation. These are references used in this presentation. Thank you very much for your time and attention.